Okay, so now we need to introduce the topic of atomic orbitals. So atomic orbitals are places where electrons exist. So this was explained to us in the 1920s mostly by a group of scientists who came up with the concept of matter that was called quantum mechanics. And it explains how the electrons exist in specific locations and not in other locations, okay? So the places where they exist are called atomic orbitals. Now, the type of orbital is identified by its shape. And so you're going to be asked to recognize, oops, got something missing here. You're going to be asked to recognize s orbitals and p orbitals. That's basically all we're going to do this semester. No d orbitals or certainly no f's. But that doesn't mean it's easy. So let's go here. Let me grab a marker and say that this is an s orbital, and it's s because it's spherical. All right. S doesn't stand for spherical, but it might be a decent way to think of it. That's an s orbital. And this is a p orbital. Specifically, can you see that this is along the y-axis? We might call this p sub y. This is also a p orbital, and usually we just call it a p orbital. If we were going to be more specific, we would call it p sub x. And this is also a p orbital, okay? So an s orbital is spherical. It's spherosymmetric. That means that it's a ball that's centered on the, if we're thinking about it like a Cartesian coordinate system, there would be an origin, would be center of the ball. But p orbitals are not like that. They're the center of the p orbital is a node right down here at the origin of a Cartesian coordinate system, right? And so there's a lobe up here and a lobe down here. Now we oftentimes will color these as red and blue, but it turns out that that's just to help us keep things separate, right? So the quantum mechanics, the math that describes this location up here is different, slightly different than the math that describes this location, but the electron density in them, as we see it here, is the same, right? So you just think of this as two blues. The one last thing I'd like to point out here is that there's only one orbital here, and there's only one orbital here, right? So this is one orbital, two lobes or areas of electron density, but there's only one orbital. So if two electrons can fit in here, there's only two electrons that can fit in here total. And it's not that one goes here and one goes here. They both go both places. Okay, so there's only two electrons here in this orbital, two here and two here. All right. So, and it's good, and we're oftentimes going to be thinking about atomic orbitals really as like a cloud of electron density. Okay. And it turns out we draw these things here, and this represents about 95% of the place that electrons can be. Now, let's talk about how we fill these guys up. So let's go over here, and if we fill these up, if we fill these orbitals up, you probably recognize this kind of notation here, right? So if we're talking about how electrons go into a hydrogen atom, we would say, well, the electrons go into a hydrogen atom, and we typically draw a little arrow for spin, okay? So there's only one electron in a hydrogen atom because it only has one proton and it's neutral, right? A helium atom has got two protons, and so in order for it to be an atom or neutral, it has to have two electrons. So we would say 1, 2, okay? The next question is, how do we know where these guys fill in here? And you got this in Gen Chem, but let me go back over here and remind you. The off-ball principle tells us that the lowest energy orbital is filled first. The lowest energy orbital is filled first, and that's the off-ball principle. You don't need to know the name of that. I just want to remind you that there is such a principle. You're probably used to drawing the electrons in the lowest energy orbital first. So let's go back over here. In that case, for lithium, I put the first one here. It's going to be 3 electrons here total for lithium, right? Because it's got 3 protons. So there's the first one. Okay, let's go back over here now. The second principle is that the Pauli exclusion principle, and that is that each orbital has a total or a maximum. I'm still in blue, yeah. Has a maximum of 2 electrons. That's the Pauli exclusion principle. There's more to it, right? But this is what we really need to know. Each orbital has a maximum of 2 electrons. And so if we go back over here, we'd say, all right, lithium, it's got 2 electrons there, and then the lowest one gets filled first. That's the off-ball principle, so it looks like we're going to go there for lithium, right? All right, and then finally, the last rule that we need is Well, let's go back over and finish these out. So beryllium's got 4 electrons, right? Because it's got 4 protons. So it'd be 1, 2, 3, 4. And boron's got 5 electrons, so it's going to be 1, 2, 3, 4, 5. Okay? And carbon's got 6, so it's going to be 1, 2, 3, 4, 5. And the Pauli exclusion principle says that I need 2 electrons in. So I'm tempted to put one here, okay? But that takes us to our last principle, which again, I realize you may be used to this already. And it's this, Hund's rule. And Hund's rule says that a degenerate orbital degenerate means equal energy, okay? I don't know why we use this term. It sounds like a bad term, right? But orbitals of equal energy all get 1 electron before any gets 2 electrons, okay? So going back over here, then we would say, well, you see these are all in the same energy level because this is energy, right? So carbon must have 2, or carbon must, each one of these guys is going to get 1 before any gets 2. So nitrogen's going to look like this. 1, 2, 3. Boom, 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 boom. 1, 2, 3. Oxygen's got 1 more. So that's going to be the electronic configuration for oxygen. All right, and that is what we're going to need to know about atomic orbitals.